When researchers analyze deep learning systems, the conversation revolves almost universally around optimization and gradient descent. Ask an engineer why they include layer normalization in a model, and they will tell you it stabilizes gradients during training. Ask about residual connections, and the answer is that they provide a clear pathway for those gradients to flow backward through deep layers. These linear algebra explanations are completely correct. They precisely describe the numerical mechanics of how a model adjusts its weights. However, this mathematical vocabulary limits our understanding. Equations trace how a tensor changes numerically, but they offer zero insight into what the tensor actually represents semantically. This creates a practical blind spot. Within a model's latent space, two vectors can differ massively in their numerical magnitude while representing the exact same semantic concept. Linear algebra struggles to explain why meaning persists when the numbers diverge. To bridge this gap, we can look to a branch of formal reasoning known as modal logic. Instead of tracking how a tensor's values change, modal logic asks a distinct question. What underlying information remains necessarily true despite continual numerical transformation? Applying this framework allows us to examine the standard transformer architecture as a series of modal operators. Each component manages the transition of semantic truth from one layer to the next. Adopting this alternative lens forces the scientific conversation away from the mechanics of optimization, focusing instead on the actual nature of representation. To test this, we evaluate a single latent vector inside a network layer, pausing the process immediately before a normalization step. This animated diagram tracks two simultaneous operations. On the left, we have vector x, an activation vector containing the values 2, 4, and 6. On the right, a completely different layer produces vector z, containing 20, 40, and 60. Every activation is exactly 10 times larger. Despite the extreme variance in absolute magnitude, routing both through layer normalization produces an identical normalized array of negative 1.2, 25, 0, and 1.225. The engineering interpretation concludes that the values have simply been statistically centered around a mean. The modal logic interpretation asks a deeper structural question. Why does the network treat two entirely distinct numerical states as the exact same semantic object? The visual data provides the answer. In both starting vectors, the mathematical spacing is equidistant. The structural truth that the lowest value precedes a middle value, which precedes a high value, is perfectly identical in both. Formal modal frameworks divide data into two categories: contingent information and necessary information. The absolute numerical scale of the vector was contingent. It did not define the concept, so the model discarded it. The proportional relationship between the numbers was necessary, and the model aggressively preserved it. Layer normalization operates as a semantic filter. It collapses multiple possible numerical worlds into a single invariant truth. Contextual operations follow the same pattern. Batch processing is almost always dismissed as a strategy for hardware efficiency and statistical smoothing. Viewed modally, a single sample inside a batch lacks isolated meaning. Its representation is actively defined by its measurable difference from every other possible state present in that specific batch. Moving up the architecture to the attention mechanism, the standard engineering description relies entirely on computing weighted similarities between queries, keys, and values. Attention resolves a severe semantic problem. Words rarely possess fixed meaning, independent of their surrounding context. Any single latent vector entering the attention layer occupies a landscape of multiple equally valid interpretations. Modal logic models these individual attention heads as parallel evaluators. They simultaneously test multiple competing possible semantic worlds. Each head navigates different contextual possibilities, searching to see which structural truth aligns with a broader pattern of the data. The final weighted combination output by the layer is simply a model converging on the specific interpretation that satisfies the surrounding evidence. Attention functions as an active search mechanism, navigating a vast landscape of semantic possibilities to locate the truest structural representation. Between these attention blocks sit the feed-forward networks driving the vertical flow of data through deep architectures. Conventional theory treats these layers as continuous, non-linear transformations, executing operations that completely overwrite the previous latent coordinates. The modal alternative suggests a feed-forward layer proposes a newly refined possible world. It iterates on a concept rather than destroying the previous state. This process is mediated by residual connections, components exclusively credited with preventing vanishing gradients by bypassing layers entirely. This animated diagram illustrates a vertical stack of transformer layers. While the outer vector shape alters at each block, a static core of nodes bypasses the transformation. In modal terms, this pathway preserves necessary identity. The feed-forward network explores new chaotic possibilities, proposing alternate interpretations. Simultaneously, the residual pathway carries forward the specific semantic structure that has already proven to be true. This dual mechanism accounts for why Cosine similarity remains meaningfully stable across different depths of a network. The residual pathway protects the core concept, while the feed-forward blocks test new representations. The hidden layers of a transformer do not execute a simple sequence of numerical overrides. They perform iterative reasoning to progressively refine structural invariance. Modern neural networks manage a dual reality. They perform brutal numerical optimization while intricately preserving semantic representation. Acknowledging this reality addresses a massive 20th century divide in AI research between two warring philosophies. The first camp, symbolic AI, explicitly modeled intelligence through formal logic, rigid rules, and direct semantic relationships. It excelled at logic, but failed to learn from raw, messy data. The second camp, Connectionist AI, abandoned explicit logic entirely. It learned statistical representations directly from massive data sets, ultimately producing modern, large language models. The ultimate irony of the modal perspective is that we are now relying on a tool from the symbolic tradition to explain the internal success of connectionism. Look at this side-by-side comparison. Modal logic functions as a complementary vocabulary to linear algebra. It maps the same transformation journey through a representational lens rather than a numerical one. Statistics and optimization govern how the model learns. Formal logic explains what those learned representations actually mean. This distinction changes how we view model updates. Fin-tuning often produces significant behavioral shifts with only minor parameter changes. Instead of measuring statistical drift, a modal approach asks which semantic invariants were discarded during those updates and which were preserved. As neural architectures become increasingly massive and their operations more abstract, tracking raw weights and numerical activations reaches a hard point of diminishing returns. Optimization explains how networks train and converge. Formalizing the semantic invariants that survive that process provides the language needed to understand what those networks are actually learning.